Good evening, everyone. Hello. Welcome to tonight's AES lecture. Thank you all for coming. I think this is probably the most well-attended AES lecture that we've had in many years. So first of all, thank you from Meridian for sponsoring the venue. Maybe we should have got the next size up. And also thank you to Bob and Peter for coming this evening. First thing, I will be handing around this to make its way round. If you could just pop your name and company and whether you're an AES member or not, then that'd be really handy just to keep track of attendance. So I'll start it over there. Thank you. So you probably all know Bob and Peter. They don't really need much introduction, but Bob started Meridian in 1977 and went on to great things and invented the first audiophile CD player in 1985. 84, excuse me. Older than I am. And Peter Craven has obviously worked with Michael Gerson and developed the Soundfield microphone and so on. But that's enough from me. So I'd like to hand over to Bob, first of all. Thank you very much.
All right, thank you. Good evening. Can you hear me okay? That's lucky, because I don't speak very loudly. So, yes, Peter and I actually have worked together since 1972, on and off, when we met at the Oxford Tape Recording Society, where I showed up to give a lecture on something that was, I think, actually, in retrospect, fairly spurious. But anyway, since then, we've done quite a lot, but we've never done this before. We've never actually given a lecture together. So, you know, sometimes it takes a while to get around to things. This is how we're going to attempt to do it. There's quite a lot to talk about tonight. I have no idea how we're going to fit it in, but we're going to zip through. I want to cover some topics in psychoacoustics and neuroscience. I want to give a high-level discussion of just a few points in digital audio coding, and then we'll look at the signal properties of the signals that we're trying to encode. And then I'll talk a little bit about a new direction. And then Peter is going to illustrate one of the elements of something we've been working on furiously for the last couple of years. And then I'll end it. And we know how long we've got, and let's see if we can do it. Okay, so the first thing, and you realize that this is just touching on the high points, because what I want to do is just pick up a few things that are relevant to the story we're about to tell. Psychoacoustics, as you all should know, is the science that bridges engineering with our experience of sound. It's a subject that I hope, as audio engineers, you've all studied in some depth. And this is a 2-minute revision. You know, psychoacoustics is really about how the sound reaches the ear and what the behavioral response is to it. You've seen these sort of pictures before many times, the outer ear, the inner ear, and the cochlea. I'm going to be talking about that. In the cochlea, we call this the peripheral auditory part, is where sounds are encoded. Sound enters the round window, travels along the basilar membrane, and is encoded by neurons. It's encoded on a loudness and pitch basis. So the first transduction that happens on going from analog, if you like, to digital in hearing is in the nerve cells in the cochlea. And as sound travels along the basilar membrane, it's dispersed from high frequency to low frequency. And in the case of the human, from about 16 kilohertz down to about 20 or 30 hertz. Cochlea is a very familiar structure in all animals. In fact, mammals have different sizes and different ranges, but they pretty much work the same way, and also in birds. Now, the sound is spread out in frequency and in loudness. Loudness is the perceptual attribute of volume, of intensity. And the neural code gives a specific loudness, and the frequencies are dispersed according to a filtering function. That's the way we conceptualize it, because there's not really filters there, but sound is filtered into a waveform along the basilar membrane. That's how we get frequency and loudness. And of course, there's temporal encoding of sounds. Sounds start and stop. Unlike in our laboratories where 1 kilohertz plays all day. Right? The real world, everything starts and stops. It's only when sound changes that, in fact, it's interesting or meaningful. And the sound is encoded for starts and stops in the cochlea and then transformed as it travels up the neural pathway to the brain. Temporal encoding is sharpened binaurally, and we can phase lock frequencies below 800 hertz. We know these things. The human hearing system is fundamentally nonlinear. That makes it really, really, really hard to do things that we like to do, like listening tests and proper experiments, because it catches you out at every moment. There are a lot of different ways in which it's nonlinear. For example, intensity and loudness are not coded linearly. There are behavioral thresholds. Sound grows as it gets louder, but in a nonlinear way. Frequency and pitch are not linear. We can double the frequency, but we don't necessarily hear an octave shift through the whole range of our hearing. That's why piano tuners get paid what they get paid. The frequency response of our hearing system is not flat. There is distortion introduced, but not a lot, and it's not a trick. But we do know the distortion exists, so we don't hear it. There's thresholding and there's masking. The presence of one sound can prevent us hearing another, either at the same time, before it, or after it. The great thing is that superposition can't be relied upon. So if we say percept A, percept B comes from stimulus A and stimulus B, we can't add these two stimuli together and add the percepts. It doesn't work like that. We have completely nonlinear behavior in terms of how we hear things. There's an example of nonlinearity. Normally it doesn't jitter like this. These are the equal loudness curves. You have the range of hearing. We have the behavioral threshold up to 20 kilohertz, very sensitive around 4 kilohertz, and loudness grows more evenly in this region than it does at low frequencies. Really, because low frequency threshold is interfered with by noise in the body and in the system. Nonlinear frequency scale I talked about. Along the basilar membrane, then, we have these so-called audio filters, which we conceptualize, and we use it in some of our modeling. There have been many estimates of the width of it. Earlier ones by the German psychophysicists came up with this green curve, showing at low frequencies the filter width of about 100 hertz. The Cambridge group, Greenwood and Moore, came up with a lower estimate. I'll come back to this later. Another thing about the auditory filter width is that it's nonlinear with level. The tuning of the filter degrades as the sound gets louder. And the presence of these filters does cause, oh, that was interesting, does cause masking around sounds. So I hope we're going to not have that problem for long. You know, okay, clearly that slide's got a timer on it, and I'll keep going. You know what I was going to say, that slide was all about MP3 and AAC and hiding the bits that you think aren't important, but actually there's nothing that isn't important when it comes to listening and sound, yeah? So, we have two ears. The peripheral function of the two ears, obviously they're spaced, they're a distance apart, that's important. We have two ears so we know where sounds are coming from. And particularly in azimuth, where they're coming from. But when sound arrives, we've got 0.7 milliseconds maximum difference in arrival time between the ears. The pinna affects, sounds arrive, we rarely hear anything once, because when a transient arrives, it's reflected on all the structures of the pinna and arrives in the cochlea many times. In the frequency domain, we see this as providing notches and an uneven frequency response. But the pinna is very, very important to know where sounds are coming from. So the frequency response changes with azimuth. At low frequencies, you can't really tell where sounds are coming from. But at various high frequencies, there are deep notches caused by the cancellations of the pinna. It's the kind of thing that gives us a clue about where a sound's coming from. That's an interesting picture, but we would say it's a somewhat old-fashioned viewpoint from what we're coming from, because this is a frequency domain view, and in fact, the important thing is the sound arrives many times. Now, we have central binaural processing. As the signal travels from the cochlea through the brainstem, we get substantial increase in temporal acuity. It's a large number of nerves. I've got a slide about that later. And we can actually perceive arrival time differences at 50 phon, which is the loudness level, in the right circumstances, of the region of 10 microseconds. That's extraordinary small time dimension, although it's absolutely not unknown in the animal world. A rabbit would think that was a long time, and a bat couldn't deal with this because bats can determine 1 microsecond interaural time delay using fundamentally the same structures, but with different adaptations in the wetware, if you like. So, and we listen binaurally, some things happen. We get different masking thresholds, we get masking, unmasking. Some things are easier to hear when we have 2 ears than 1. You all know that. Let's follow it up. Let's look at the ascending pathways of the nerves. So we start from the cochlea into the brainstem. Notice it swaps sides. Travels through several processes of feature extraction and sharpening up into finally to the auditory cortex. These are the basic steps that it takes. We don't need to understand them all, but one thing we do need to understand is that the cochlea, I talked to you about the auditory filters. There's about 3,600 of them spread from 20 hertz up to 16 kilohertz or 18 or 19, so about center frequency. There's another 7,000 traveling back into the cochlea, which confused us for a long time. What were they doing? You'd expect this is a microphone and, here's the amplifier and it's all understood up here somewhere. But actually, there's more nerves traveling back to the ear than out from it. Interesting. So in the brainstem, these nerves, each hair cell, we've got 3,500 hair cells, 3,600, it's not an exact number. Each of them has 10 neurons traveling from it. Because what happens in the way that we interpret the sounds along the cochlea, we're looking for patterns, movements, changes, and multiple signals to vote for time. When you have this number of efferent nerves, that's 35,000, going into what is the wetware equivalent of an AND gate, a 60-input AND gate called an octopus cell, we get radically improved time resolution. As an engineer, I like to think of the brainstem where this stuff's happening is very fast, signals come in, pre-processed. This is like the microcontroller, right? Works in real time. Up here, you've got a slower engine, which can take 100 milliseconds to make a decision about something. But here, in the primary brain, things are understood at the microsecond level. I'm now going to play you a very short recording. This is the sound of the natural world. And in that recording, we're hearing, the environment, we're hearing the distant road noises, we're hearing the birds. And where I want to take you now is into the wood, just for a minute. Because our hearing system has evolved over millions of years. And it's still stuck in the rainforest. We do horrific things to it and we abuse it, but in terms of evolution, fundamentally, that's where it is. And when you stand in the wood, and hopefully it's quiet, you will hear sounds, you will hear cracks as wood dries, as the bark dries on the trees, as the leaves dry, or as the sun dries the leaves, or as an animal moves in the leaves, or as a heavy animal snaps a twig. When this happens, you don't have to think about where that is. You know exactly where that is. When we hear a twig snap, we can point to it. We can turn and point to it. Because this stuff is hardwired into our brain. The understanding of a sound, the first question for survival is where, and the second one is what. Although I think they come very quickly together. The most important thing our ears are good for is telling us about things that we can't see, things that are remote. You want to know if it's something you can eat, or if it's a threat of any sort. So the snapping twig is an important sound, and it is utterly fascinating how precisely, not only you know which direction, but how far away it is. How far away. And a lot of that is to do, well, in the wood, of course, we have some reverberation, but some of it is also to do with the absorption of the air. So this recording that I played you has this frequency spectrum, and it's a very, very important one. In black is the average for the whole recording, but here, when the bird chirped, here it is, between 3 and 8 kilohertz, it's quite clear. But the most important part is the underlying trend, which is the 1/f characteristic of environmental sounds. All environmental and natural sounds present this characteristic. And the interesting thing is, if you speed it up or slow it down, it still sounds like an environmental sound for that reason. Right? So 1/f is important. Parenthetically, it's also important in the visual domain. This picture, and almost all pictures like that, if you walk into the woods, if we were to process that into a contrast spectrum, spatial frequency map, it will have a 1/f characteristic. And what's interesting about it is that as you walk towards the tree, even though you see different layers of detail, this kind of 1/f structure is maintained. The fractal structure in the picture. The same's true in sound. Sounds like this, environmental sounds, have a structure that we know. In that recording, you also heard vehicle sounds. That's not part of our evolution. But this sound of the animal vocalization is a completely different class of sound. It's got pitch, it's got time, it's got chirps. In fact, if you slow it down, it's singing a really interesting song. That's because his time frequency balance is different from mine. I don't get his chirps completely. But nevertheless, this type of sound is important. What's fascinating to me about the way we process sounds is you didn't know it was coming, but within less than a bar, you knew it was a piano trio. You knew where the instruments were. These two waves had arrived at your ears, and immediately you had externalized those objects, piano, cello, violin, in a location. Quite fantastic. Not only that, in a slightly more normal room, you might also have been able to work out at the end of the second note what the acoustic of the room was where the recording was made. Actually, it was this one. This is a very high-level learned behavior. I wasn't born knowing what a cello sounded like, or indeed any of the other instruments. We learn that quickly. But isn't it extraordinary, if you just stop and think about it, how our brain does that so quickly? Because in performing this act, it said, there's a piano, so we take that bit away, what's left? That's a cello. Is it a cello and a viola, a cello and a violin? Decomposing the sounds into the different instruments, of course, we use a lot of clues to figure this out. But the main thing is we perceive objects. In the wood, we knew it was a twig, or a mouse, or maybe a bear. We hear things outside us. You hear a sound, you know it's a guitar, you know it's a singer. This type of sound, music sound, is third class of sound. Actually, it's a fourth class of sound, because speech, environmental, animal sounds, speech, and music kind of lives in the middle. Probably, I suspect, because it came last. Music was evolved to use our ears rather than the other way around. Whereas our ears definitely had to know about the rainforest. So the things that we use to perceive objects, the size of the sound, where is it? Frequency, it's fundamental. What's the timbre? Things that are moving together can be grouped together. So we have this concept of auditory streaming. If things start and stop together, if they correlate, if they have continuation, they become an object. The extraordinary thing about high resolution, which is the first time we've talked about it tonight, is that the more information you get of the right information in the sound, the easier that is to do. The simpler it is to form that percept, that externalization. When that's the case, it's easier to enjoy it more, which actually is the point of what we do, is to enjoy the sound more. So we perceive objects. And as we listen, the sound begins, the first note begins, and it moves into our auditory memory, which is about 6 seconds, and it moves through 3 or 4 what we call conscious presence, the sort of, you begin to build a picture. If the sound is quiet, we may have trouble working out what it is. But basically, this is a hypothetical decision tree of what's going on. We know it's a keyboard, we know it's a piano. It takes us a bit longer sometimes to work out what size of piano it is. It might take you 6 bars to work out if it's a Steinway or a Yamaha or even a Fazioli. This slide's so old, Fazioli didn't exist. But this is what our brains do. That's all part of the higher order processing, extracting the objects. I'm going to skip that. So, when we started, the auditory sciences consisted of psychoacoustics. And it served us well. What's been really exciting in the last 10 years is how neuroscience has exploded as a discipline that gives us insights into some of the things that have puzzled us for a very long time. Psychoacoustics tells us what it does. Neuroscience tries to tell us how it does it. And it gives us a second framework. We've got engineering framework, we've got psychoacoustic framework, and here we've got a second framework from neuroscience to ask questions and to do modeling and I don't propose to explain all of this, but the biggest thing that's given us insight into how some of these things are happening, like what and where, the formation of objects, has come from imaging. PET, functional MRI, and so on. Now you can put somebody in an MRI machine playing piano trio, and look what happens, which is fun. And also gives us a lot more information about where we can see things moving from the memory to the parts of the cortex, the auditory cortex, which gives us that analysis of sound, recognition, speech recognition here, sound recognition there, or varying sounds moving. The nerves that come from the cochlea don't just code frequency and time. They also code when things are changing. Frequency is rising, there's a different neuron lights up. If it's falling, a different one lights up. Mapped into different parts of the brain, pitch and so on. But the most interesting thing that happened in the last 3 years was that we saw reports in Nature of the where place and the what place as being completely different parts of the brain. What is it and where is it? And where is it is mapped very closely to the visual space. Interesting. What does it tell us? Well, so I've talked a little bit about the neural paths. This is a cross-section through the cochlea, through the basilar membrane. So sound impinges on this, and the tympanic tectorial membrane here moves as the wave travels along the cochlea. I touched on this earlier. We have between 3,400 and 4,000 inner hair cells, which are the microphones. They feed signal straight to the auditory nerve. They go up the pathway. Those are the ones that cross sides and are multiplied by 10. The nerves coming back here to the outer hair cells connect to these 3 sets of transducers. So each inner hair cell has 3 outer. That's very odd. The outer hair cells have 2 sorts of nerves too. We have nerves coming from the upper process, from the cortex into it, and there is some efferent up to the brain. We believe, or we know, that the main function of these is to act as an amplifier. This is what's called sometimes the cochlear amplifier. These cells, in response to stimuli, will change their length. And that's one of the reasons we have such a spectacularly good behavioral threshold. Not quite as good as the cat, but our hearing threshold gets down pretty much to the point of Brownian motion. This amplifier adds positive feedback, so sound comes in and encourages it, so we get this higher Q tuning at every point on the basilar membrane. This is the part that's often damaged when you're subject to intense loud sounds. So these outer hair cells, very interesting. And some of these numbers I've mentioned earlier, 3,500, okay, we'll go with that number. Each has got 10 neurons to the brainstem. 10,000 outer hair cells. Temporal accuracy is increased in the octopus cells in the brainstem. Each one has 60 inputs. So this is analysis that's been done by several people. 125 microseconds is the basic uncertainty of firing of a neural spike. As a stimulus, you've got an uncertainty. When you have 60 of them, the uncertainty falls by root n to 16 microseconds. They then feed the Bushy cells for a time, and the uncertainty drops to 8 microseconds, which is about the same number that we see in the behavioral study of the sound, the time differences we can hear between our ears. Interestingly, acuity to time is not related to frequency. As engineers, we're accustomed to the idea that, say, if you had a filter at 18 kilohertz, so its time response is approximately 1 over 2 pi 18. The human hearing system has approximately twice the acuity for time as it does for frequency. So that's one thing that's interesting. Second thing that's interesting is that as our hearing degrades, generally speaking, you can hear higher notes when you're younger and haven't discovered alcohol and girls than you can hear later in life. And for some people, that declines rapidly, and some people it declines rapidly because they abuse their ears, like they play in a rock band, or you go shooting and you do things like that. But because our basilar membrane is laid out logarithmically, if we look at someone who's lost their hearing down to 9 kilohertz, so you've got 1 octave gone missing, you would think that would double the time resolution, but it doesn't. You've only lost 10%, which means that in terms of time acuity, somebody who can't hear quite so high, if you can hear to 9 kilohertz, you might have between 5 and 7% reduction in time acuity. Now this is interesting because we see that behaviorally. Some people who hearing is more difficult can definitely tell where things are coming from. And we've, in our adventures in the last couple of years, come across quite a few band musicians whose hearing is shot through standing in front of loudspeakers for too long. To hold a conversation with them, they need a hearing aid to get the consonants, but they can tell you every time if you're playing them 96K or 44K digital audio, because the timing is different. So, that's just a little bit about how we get the precision. And I talked earlier about the descending neural pathways from the cortex down to here, because there's something else going on. It's not just saying, turn it up a bit, amplify it. Peter's sitting here thinking, he wishes he had a microphone that he could adjust like the cochlea, you know, because one of the other signals that comes down here is to change the Q of the filter. The reason that we have 3 outer hair cells is we can drive them differentially, and we can make the ear extremely selective when we're attending to speech, particularly a cocktail party or something like that, listening to speech. We can make it narrower when we want to listen for animals. So wide when we want to listen to animals, and extremely wide when we want to hear the environment. This wasn't understood that this could happen. That when we say, listen to that, you're actually doing something subconsciously of retuning the transduction in the cochlea itself. So these filters are modified in real time. Okay, now I'm going to, little diversion, it's on the same topic, but I want to give you just a quick overview of what I think is one of the most seminal pieces of work to come out of neuroscience modeling in the last few years. This comes from a man called Lewicki from the University of Calgary, 2002. His proposition was that we could understand more about how the hearing system works, knowing that there are filters and knowing that each filter triggers spikes, by trying to encode using filters like that and spikes, a spike code, right? So rather than using an FFT or any other wacky thing we'd like to do to make a lossy coder, let's try and code it like the brain does. And taking the different classes of sounds, environmental sounds, animal vocalizations, and speech, and training the model to produce the minimum number of spikes and the maximum and the lowest signal-to-noise ratio, they were able to come up with filters that look like this. Now that is a pattern of different nerves firing in response to an environmental stimulus, the sound of the outside. This is when the bird starts to sing. And this is when people are speaking. And you'll see that the filters are different. They have different impulse response, in a sense, if you'd like to say that. And here is what's actually measured at the auditory nerve if you probe it. You don't get to do that a lot, but there are times when it's allowed. And you'll see that the model predicts very accurately the kind of things that are going on. What this shows is that the way we analyze time and frequency in the ear, sorry, it doesn't show it, it hypothesized that is not using a Fourier analysis. Fourier analysis, we have very, very precise discrimination of frequency and very poor discrimination of time. The really good thing for the ear was that it came before Mr. Fourier and doesn't have to know about things going on to minus infinity and plus infinity. And if we use a wavelet transform, where we get different frequency and time, different time discrimination at higher frequencies and lower frequencies and so on, you get a different kind of pattern, which is relatively efficient, much more efficient than Fourier, but nothing like as efficient as the filter populations that we see here for the environment sound and the animal sounds, where we have extremely tight tuned filters, and for speech. Here's the extraordinary thing. Take the speech filter bank and say the word canteen. I don't know why they chose that word, but maybe they were hungry. Into it. And with extreme precision, the whole word is coded with 60 spikes. Not 350 kilobits per second. 60 spikes for the word. And the residual is extremely low. So this kind of modeling, this kind of insight, helps us to understand maybe what are the important bits of things, what we don't want to throw away, what we need to preserve. Turns out, you see, humans twice as sensitive to frequency as to time than frequency. That was unexpected. And we need to understand how the sound is best presented to you. Because, as we'll talk later, everything is lossy. Just an example, quickly, comparing encoding these sounds with the spikes and the filters. With Fourier, it's 10 times as effective. Data rate's 10 times higher. So Fourier would have actually used 600 spikes. Each spike is worth 2.63 bits. So somebody else can do the math. This model predicted that the auditory filter bandwidth would be different for the three classes of sounds. Environmental sounds, 150 hertz, from which you could deduce that the outside is German. But speech, come up with a very low number, much lower than the Cambridge team came up with for the width of the auditory filter. We'll draw a circle around that because it's interesting, because it may tell us that we have to change our masking models for lossy codecs, and it has to tell us about different behavioral noise floors for noise shapers, things like that. Because what the psychoacousticians haven't constructed an experiment to do yet is to measure the bandwidth using these different signals. In fact, neuroscientists say those guys, they use tones and hisses and beeps. People don't listen to that. They listen to these other sounds, and you have to train your models using the real sounds. Our target, then, in terms of recording, I brought you here to talk about high resolution, not about sound, but I think it's important. Our target is to reproduce the sound of the original. It's not about analog and digital. There's a sound captured in a microphone, goes through an amplifier, to another amplifier and a speaker. That's the shortest chain we can make. That's our target. It's already wrong, of course, because nothing's perfect. The microphone's lossy, and the speaker's lossy, and the amplifier is certainly not a straight wire with gain, but in the context. The only thing we can get hold of is this signal. Because nothing's perfect, no steps that we perform are lossless, the best we can aim for is transparency. So when we work on a signal, when we modify it, if we store it, we want transparency. And by that we mean it is possible to change the sound but not damage it. One of our yardsticks for how much you're allowed to damage the sound is it's okay if all you do is the same thing that air does. So we would say that a reproduction system is allowed to make you think you're 2 or 3 feet or a meter further away from the source. And that's quite a good yardstick. This is showing us the attenuation of sound, standard temperature and pressure. Now, let's look at it at 10 kilohertz. The good news is, at 3 meters, it's all right. 10 meters, we've lost a couple of dBs. So the sound is dispersing. That's why lightning strike sounds sharp here and like a boom when it's a mile away. Sound disperses through this because it's actually the carbon dioxide in the air that's predominantly causing the absorption. And interestingly, that means that if you were transported back 300 years, things would sound closer. However, we adapt to it. If you are 30 meters away, we've lost 6 dB at 10 kilohertz, and we've lost 24 dB at 20 kilohertz, which is why you don't want to sit at the back of the concert hall. However, this is what air does, and it's a useful framework. Now we're going to look at what happens to the chain. Sound comes in, microphone does its work, preamp and so on. Every step that we perform will change the frequency response and will blur the signal. There's a straightforward optical analogy of blur. Right? Let's take a second order Butterworth filter at 30 kilohertz. Why? Because this is what the BBC recommended in the book that I read when I was a schoolboy. The wider you open the window, the more dirt comes in. If you're designing a box, young man, you know you better make sure it doesn't go too high, and let's roll it off tidily. This kind of thinking is embedded in audio engineers. So the guy designing the preamp, one designing the, what's up? Wrong frequency?
It looked like 20 kilohertz filters.
30 kilohertz filters.
Is that...
No, this is not increasing order. This is cascades of second order. Okay? So we get progressive high frequency reduction, of course. Why would we even think about this? And the answer is because by not thinking about it, the microphone's doing it, its preamp might be, the mixer probably is, the recorder probably is, the A to D converter almost certainly is, the DAC, you get the picture. And we have this cascade now. Not everybody will do that. But in the middle, if we decide we don't want to go at 44, we want to go at 192, we will get a difference, but the difference we're going to get is going to depend dramatically on the rest of the chain. How much does the chain blur is in fact the important parameter. And then we're working on high resolution, which we've been doing. You go at higher and higher speeds, your chain has to be better and better, your microphone has to be better, you have to take great care that you've got 200 kilohertz bandwidth here, there, and everywhere, in order that the analog part isn't blurring more than the digital thing you're trying to figure out. What happens to the time response through that chain? Even if we start with a perfect impulse, you'll see that the impulse gets wider and wider until it gets quite embarrassingly wide 30 microseconds is the shortest thing we can describe, which is 6 times longer than the difference we can hear. It just compares air to the filter. Okay, now let's look at the signals that we're looking at. We've made an analysis of high-resolution recordings, so the whole corpus, things from studios, different studios, things we've downloaded. Looking at the peak level in the recordings, you see a picture. You see a picture that, and we know this, of course, that at high frequencies, and at progressively high frequencies, there's less and less of it. This is self-similarity. This is like the environmental sound. Different recordings behave differently, but this is invariably true of music, all except for one piece of music, which is down to him, which we'll explain later, which has an extremely wide energetic frequency response. But you'll see that we do have signal at 24 and we do have signal at 48, and it depends what it is. This is everything from analog tape to modern digital. And this is analysis of the noise floor in those recordings. We've struggled really hard to find quiet noise floor recordings. Miles Davis here. Okay, there's a line. This line is the 16-bit dither line. There's a point to this which we'll get to, but generally speaking, recordings do not go below the 16-bit noise floor. There are a couple. There's one here done by Tony. There's a couple here done by 2L in Norway. Special odd recordings, but we can't find anything that gets down to the 20-bit level. And there's a characteristic to things that we like to listen to, the music we'd like to hear. Whether it's Ella, this is the noise floor of the analog tape machine, and this is the peak level. Here's something we'll play you later, which is a recording from 2L of a piano, noise floor and the peak level in the recording. Recordings tend to have the similar property, which is somewhere the signal meets the noise. It can sometimes be below 20 kilohertz. Usually it's not. Very, very rarely, indeed, is it above 48 kilohertz. And these clusters, different recordings of what we'd like to think of as triangular spaces of information exist in the recording. So we've got a 192 kilohertz recording, 24-bit, maybe it's 32-bit. That's a lot of data, but what's inside it is the important bit. The information inside the recording, which is not the data in the recording, tends to have this shape, which is not unlike the shape of something between animal vocalizations and environmental sound. This is another example of a recording. This is 176. This is take 5, which had the severe misfortune of having been encoded in DSD. And the no longer required supersonic noise, because it's in the PCM domain, hangs around to haunt us. But this converges, at 36 kilohertz. It's probably better if we get back to the analog tape, which is going to happen, but anyway. I just put that in again just to remind us about 1/f. The digital promise then was to take that chain and to try and be transparent and stick something in the middle. Why do we want digital? Simple. If we can convert sound to digital, then we can transmit it through time or space. Playback can be repeatable, and with care, it can be transparent. And converters, the A to D converter and the D to A converters, where a lot of the evil lives, are the gateways to success or failure. If we convert it to digital, then that happens. When we convert to digital, in PCM world, we sample in two domains. We sample in the time domain, take the waveform, sample it at intervals, and we sample it in the amplitude domain. Quantize it. That process gives us samples and gives us a quantization distortion. Quantizer wanders up in 1 LSB steps, and if we do not dither the signal, then the lower it gets, the more and more distorted it becomes because of the impact of the quantizer. This error, which is plus or minus 1 LSB, is a constant error and becomes more and more significant as the level reduces. I think I'm going to play you an example of that. First, I'm just going to play you piano notes. And now, for the benefit of you in the back, I'm going to turn this into an 8-bit system and not dither it. So we'll quantize this at the 8th bit. It's entirely equivalent to being played quieter. And if we turn on basic rectangular dither, this is what we get. The distortion isn't so bad, but it absolutely has structure. The noise changes with the signal. We call that modulation noise. Modulation noise is bad. If we do something slightly more sophisticated, I'll play it with the dither subtracted. Point of that test was not to illustrate necessarily dither, but this is something that has been known about since the late 80s, and there's fundamental papers were written about it again and again. It's been talked about, and yet, even today, people don't use it properly. You know, there's triangular dithers or shaped dithers, higher order dithers. Again and again, we see it in the studios. You watch a process, a lot of things to be done. Now, what you're supposed to do is every time you make any change of gain, you're supposed to dither if you requantize it, or you work with big words. But again and again, we see work that goes all the way down the chain, and then you say, well, I'll dither it at the end. You dither at the end, you're not only not fixing the problems, you're embedding the problems that were introduced. So fixing the mix doesn't work. And the other area where it comes up a lot is in A to D and D to A chips, where the manufacturers of the chips don't want to put dither in necessarily because it spoils the specs. So maybe we wrap the error around and we'll have some noise modulation, but it'll be fine. And it's one of the limitations to real-world digital audio is the converters having still quantizing errors in them. Now, the good news is, I showed you at 8-bit, and if you got that wrong at the 16th bit, we'll get an error, and this is a 1 kilohertz tone because we're engineers. And there's the distortion, and this is the behavioral threshold. We hear the distortion very clearly. If you work at 20-bit, at 24-bit, the errors, you can get away with it, but that does not mean it's not there. We can hear it at the 23rd bit on the right tests. Okay, so quickly now. Classic sampling. I've shown you the quantization. In terms of frequency, we take samples at points in time. Sampling theorem says signal contains no frequencies higher than fs over 2. It's completely determined by capturing at fs. We all know that. And the basic function is the sync function that gives us a rectangular window of frequency. Here we go. Rectangular frequency domain. We have a sync function. The impulse response of that filter, which is the gateway, and if you remember right at the beginning of the digital bit, I said if we can turn this into digital, the first thing we got to do is pass it through that anti-alias filter, and at the end we have to put it through a reconstruction filter. Filter could have this kind of characteristic. In the perfect sync, Mr. Fourier got involved, and it goes back to minus infinity. In the real world, these filters are windowed, but still they have a very long impulse response. And the worst thing that can happen, that happens with them, is the sound starts arriving before it's begun. We hear the ring, and then we hear the sound. And this leads, when it's done badly, to high frequency sounding splashy and bright in the digital system. 4 milliseconds long impulse response. Some companies have 10,000 taps, which is even longer. 4 milliseconds, it's this long. Our twig snap is this big. So when we hear it, we can't actually tell exactly where it is. We can use different sampling kernels. I think Peter will talk about this later. If you were trying to record perfectly for the future generations with no regard for data, we could use a Gaussian kernel, which has a very soft frequency response, but providing you go fast enough, let's 700 or kilohertz or megahertz, you get a perfect balance between time and frequency. That might be the thing to put in the archive. In between, there are other things we can do. Anyway, sampling theorem had many inventors because it was successful. And basically what it says, Shannon permits 1/fs degrees of freedom. But any discontinuity comes along and it's invalid. And a lot of the signals we have are not actually band limited. They might have been band limited going in, but not going out. What is not band limited? Processing, clipping, loudness up against the rails, quantization, puts an infinite bandwidth pulse into the system. We can make it work, providing there's a finite rate of innovation. In the system, we've got two gateways, the A to D and the D to A. The typical analog to digital converter has a modulator running at a few megahertz, maybe 2, 0.8, 5, something like that, with a 1-bit modulator. The first thing that happens then it's digital is a 1-bit signal. And this was, in fact, the origin of DSD. That is then decimated, put through a filter. This one can't be dithered properly. This one sometimes is, but often isn't. But it's a decimation filter, which gives us, a high-pass filter, PCM output. There are 3 possible outputs of this A to D. The one that should be the archive, which is the output of the modulator, whatever modulator it is, whether it's 1, 2, 3 bit. A noise-shaped quantizer to give us the 1-bit output, and the PCM. We encode it, we do stuff. When it comes to playback in your iPod or your hi-fi or whatever, goes to a DAC. Typical DAC takes in PCM or 1-bit. PCM goes through an upsampling filter to a modulator because we can't make a multi-bit DAC very well. delta sigma DAC, 3 to 8 is a typical number, running at 2 to 5, sometimes 8 megahertz. This modulator is actually where the audio comes out. The 1-bit signal, true DSD, from here, goes through a decimation filter because it has to drive a multi-bit modulator. It's very hard to find matched pairs of pure PCM or pure bitstream converters. But the more profound thought is that really what we want is not to have these signals be right, but to map this modulator to this modulator. If we can do that, then we have an end-to-end integrity in the way the system operates. So the actual converters in each case, not bothering so much about the grammar in between, because really these are just numbers. The important numbers is what's happening here and here. I mentioned the sync. The faster you go, the narrower it is. That's logical. About 10 years ago, Peter published a very useful paper about apodizing, where we could have a filter which, at least at playback, was able to remove the errors of the A to D converter, but still left the problems in the DAC. But it has a much more natural response because things happen after the event. Twig snaps and the filter follows. It's not, I'm going to snap this twig and you have to know at minus infinity when to start all the other sine waves going so they cancel and then give us the snap and then cancel again. I really don't know how that works. So, high resolution. This is a graph, arm-waving notional graph of sound quality for different formats. It is observed by many, us included, artists, producers, recording engineers, audiophiles, journalists, that generally speaking, sound quality gets better with conventional digital audio as we put up the sampling rate. The ultimate, of course, is the sound of the studio, which is, if you like, pure analog. But it is annoyingly true that when we go from 96 to 192, it can get better. And even more annoying, you go from 192 to 384, it can get better. With a conventional system, one of the things that's happening is that the linear phase filters, the sync pulses, are getting shorter and shorter, but they're not actually disappearing, which is why we're on this hiding to nothing. Because as we go up here, from 44 to 96, 192, the data rate's going up like mad. We've got all this data and very little more information. It's a very, very inefficient way of conveying the better transient twig snap. And because of that, we have a blur which decreases as sample rate comes down. So let's just look at this picture for a minute. This is coding space, this is Shannon space, information space, where we're showing amplitude versus frequency on a linear scale. Here is the noise equivalent of the behavioral threshold. That's in the 2004 papers, how you do that mapping. Basically, this is representing the hearing threshold as a noise floor rather than a tonal floor. Allows us to see where we can hear. And in here is the CD channel, and here is 9624. And on it, 3 recordings. The loudest one, noise floor, quietest one, noise floor. And this curve, which everyone should know about, is the thermal limit of the microphone. Can't make a microphone with a lower noise than this curve. It's well above the 24-bit level. 16-bit is here, here's 24, microphone lives there. Even with that, it's electronics. So a slightly more sophisticated view of this then is to say, well, here's that curve I talked about, the uniform exciting noise at threshold, which is the allows us to estimate the information capacity of each of our ears at 660 kilobits per second. The CD, which misses here and here, 9624, 192.24 has an enormous coding space. And somewhere in here is the music we want, and somewhere here is the timing information we want. But it's not up here, and it's really not down here, where there's enough data almost to describe the number of atoms in the universe. 32 bits is 120 dBs quieter than we can hear. What's that about? The answer is, of course, more numbers the better. Numbers are bigger, we can charge more, or whatever. But the data rates of 192.32 is, and that's 192, not 384.
So why are we so concerned about the temporal acuity of the ear? Well, it's because there are transients. Where can we get transients from on a recording? Well, of course we can download expensive 384 kilohertz recordings from various websites, or, are we ready?
You want me to play it now?
Or we could just listen to a 78.
Now?
Yep. On that recording, by the way, that was Manuel Del Rio playing castanets in 1936, and the transcription was expertly made by Peter Adamson, who is sitting in the audience there. So thank you, Peter. On that recording, there were two kinds of transients. One is the castanets themselves, which are not hugely, they don't go to tremendously high frequencies, at least they don't on the 78, because it's unlimited to 6 kilohertz. But you also, of course, have the crackles on the disc. And I thought I'd show you some crackles, admittedly not the same disc. This is, the waveform there is Kathleen Ferrier singing. This is all a mess because the stylus of the record, of the pickup, has a resonance at 30 kilohertz. We can deconvolve that resonance, and now we can see a lot better the waveform of the audio with discrete bipolar pulses every time the stylus goes over a bump and goes first playing one and the other. Now I'd like you to notice that between these two ticks, bumps, crackles, as we call them, we can see the original audio. This is at 192 kilohertz. If we now downsample it to 44, then really you haven't got much chance of distinguishing the music from the crackle. So the interesting question is, if on an oscilloscope's trace you can't see it, well, is the ear, have you disadvantaged the ear as well? Here's another source of high frequency. In fact, Bob, you didn't show that slide from James Boyk.
It's coming, it's in your deck.
Oh, I see. Right. Okay. Well, James Boyk has a website called There's Life Above 20 Kilohertz. So it will be coming, his little list of bandwidth of different instruments. And one of the second instrument after cymbals that has high energy above 20 kilohertz is the claves. Here we have the impulse response of the claves, and if we zoom in to that very first, so we have 0 to back, and here's the start. Each one of these dots is one sample at 192 kilohertz, and it's taken 3 dots approximately to go from 0 gradient to something like a constant gradient before we go on there. So we've really got conceptually a discontinuity of gradient, which in spectral terms is a 1 over f squared spectrum, which I thought you would like, Bob.
Thank you.
All right, so what we're really here to talk about is high-resolution audio, and Bob has really said a fair bit about how can we digitize audio in such a way that we don't lose this precise timing information. And we call it the process encapsulation. Along with all the papers that Bob's talked about neuroscience, there have also been some very interesting papers about sampling which get away from the traditional Shannon idea of just doing it very regularly and limiting the frequency band. The point being that these twig snapping will happen at peculiar times that are not related to sampling instance. Well, if we have some kind of thing like waveform like that, here might be the sampling instance. They're supposed to be different colours, but, well, it doesn't matter. You can imagine that if we move, whether this lot gets picked up or not depends on exactly where it lies with respect to these, with respect to the sampling. If the sampling instance were moved along a bit, we'd see something quite big there. As it is, we don't see it, and it's gone by the time the next one comes. So it's better to integrate with a rectangular window. At least you're bound to see everything if every sample is taken by averaging over the time since the previous one. But still, suppose you have a single impulse, and you now think of this being moving backwards and forwards, and can you get from the digital samples any information about where it is? Well, as it moves forwards, there'll be no change at all. It's in that bin, and then quite suddenly it moves to the next bin, and then stays a bit, moves to the next bin. So clearly that's no use if you want to be able accurately to reconstruct where that event, what point in time that happened. So instead we have what we call infrared coding, which is also advocated in some of these highly abstract IEEE papers about recovering events with a finite rate of innovation. And the idea of that term is that ideally you'd like to be able to recover things that really are closer together than a sampling interval, but a finite number must come per second. You can't, you could resolve 2 very close together, but you couldn't resolve 20. Or, you haven't got the information to do it. Clearly, this works because as this moves forwards and backwards in time, it'll be picked up in the middle equally on those two, or you get more on that, less on that, etc. So that we call infrared coding, and it is a way of taking either an analog signal or a higher sampling rate digital signal and bringing it down to a lower rate without losing the information about where individual pulses started. Well, do we use these triangular kernels, as they're called? The answer is not yes, we do actually, and we do sometimes in encoders. It does work, but I want to. But you've seen this slide. Bob has shown it already, so I won't say it. Well, it's a Gaussian. A Gaussian kernel is a good one, except that you need to go out to about 300 kilohertz in the frequency domain in order to, before it's gone down to zero and has given you unambiguous information. You can sharpen up. I think these are in the wrong order. Oh no, they're not there at all, doesn't matter. You can take a Gaussian with its response like that and sharpen it up with a filter afterwards. So after sampling, you can then apply crudely a bit of treble boost or some post-emphasis to flatten the frequency response. If you do that, you're bound to have an underswing. There really isn't a way, unfortunately, of having a flat frequency response, getting down to zero at some reasonable frequency, and yet having a totally positive impulse response. But still, this is not too bad, because we can keep the length down to, what do we do, kind of six sample periods at 192, and sometimes shorter than that if it's infrared. In fact, this is the end-to-end. I think we have slides slightly out of order. Just let me. No, it's not worth it. Okay.
You could go back to your triangle.
Doesn't matter. We have. Yes. Okay. So we've got a frequency response droop if we have something that's positive. Everywhere positive. You can correct that later, and that creates this underswing. And this is one of our favourite filters, actually. We call it filter B, because I basically designed A, B, and C on the 17th of July 2012. And this is the one that was liked. The best balance between keeping it short and flattening the response with, so that we get droop of less than, I think, 0.2 of a dB at 20 kilohertz. Well, that is, of course, not how the industry does things. Bob has really touched on this, the use of a sync kernel. So I'll show you, if you downsample using a fine piece of software called Adobe Audition, which does things extremely well according to conventional engineering criteria. It will put the filter, as Bob has showed, a brick wall filter, a wonderful brick wall filter. It's absolutely flat to 22 kilohertz, and then it drops by, I think, 80 dB or something, quite fast. How fast? Well, if we do a close-up, it's pretty well where it started at 22 kilohertz, and by 22.1 kilohertz, it's all the way down. It's taken about 70 hertz to do the majority of that drop. Now, again, Bob referred to factors of 2 pi, and those of you who've done any quantum mechanics know about the time frequency uncertainty principle. If something's going to go down in 75 hertz, then its response is going to have a length something of the order of, well, 13 milliseconds divided by 2 pi would be 2 milliseconds. Well, there is the impulse response. That's 2 milliseconds. But what we don't know is, here are some pre-responses. How sensitive is the ear to pre-responses? Bob has explained that they're undesirable. Should we worry if they're at minus 20 dB, minus 40? I've even seen minus 80 dB suggested. Well, if we blow that up by 40 dB, we get that. We've got a lot of energy in the 2 milliseconds surrounding the pulse, and even 10 or 20 milliseconds, still quite a lot. So that is, that is really state-of-the-art according to conventional thinking. Adobe have not done a bad job. They've really done an extremely good job by normal principles. Yes, slides got slightly out of order. So this was our favourite filter as an encoding filter, and then in the context of a change from, let's say, starting from digital, going down to 96, coming back up again, what we tend to do is to apply that treble boost to flatten the response. Remembering always, of course, that 192 kilohertz is not analog electrical, still less is it an acoustic response. So in principle, you're going to have analog reconstruction, and have we managed to make a loudspeaker with a time response of 1 microsecond yet? We're working on it, I don't think we need to show that one. So Bob, I believe, is going to play you a recording that was made at, or was distributed at 384 kilohertz, a DXD recording. So that's 32 bits at 384 kilohertz. We're not going to feed those bits directly to the DACs in the loudspeakers. We're going to reduce the sample rate before we do that. So here's an analysis of the noise floor of the recording, and again we got a nice low noise floor above 20 to 40 kilohertz, as Bob was explaining, but above 40 kilohertz, massive. And I'm not quite sure why that is, because D to A converters, A to D converters do have a rising noise floor, but perhaps not quite that fast. And as it's DXD, not DSD, there isn't really an excuse. Anyway, all we can do is to take the recording as it is, and I believe this is typical of many DXD recordings.
It's got an 8-bit one.
Oops, what's happened here? So there's the noise floor. I fitted a model to the noise floor, and then, so you see, if we were to reduce the sampling rate to 96 kilohertz, all this stuff would fold down back. If we did nothing, if we just decimated, all this stuff would fold back at full level into the audio band, and it would be terribly hissy. On the other hand, if we pull it down too much, then we're extending the time response. So we can use boat-shaped phase shift theorems and various other bits of maths to work out what is the optimal curve that will keep the noise below the noise of, well, the original recording or something like that, with minimal time blur. And Bob, I think it's time to go back to you.
I'm going to make this really quick. Last 5 slides, if I can count. Thank you, Peter. I mentioned end-to-end, and I mentioned the fact that the A to D and the D to A, it would be good if we could join the modulators together, because this is the real place of action. In between, we can have a big argument about whether 192 or 384 is better. Actually, these are just numbers describing the transmission path. It's kind of arbitrary how we take the modulator output and send it forward and transduce it at the end. It's a matter of convenience. because we haven't taken a structured view as an industry, because we haven't said the DAC has to match the A to D, rather than we say, here's the file, play it on whatever DAC you like, right? Then we end up in this chaos where everyone's free to choose their own methods, and you don't get optimum methods. So we can get quality and efficiency improvement. Efficiency you could understand, but quality is quite surprising. By standardizing both ends of the chain, using the right anti-alias and reconstruction kernels, we have to bury control information into it because we have to tell the decoder what we did in response to the signal. We call the process of taking all the data of the high-resolution file and extracting the bit we can hear, encapsulation. This is different from taking the audio you can hear and taking away the bits we think, rather arrogantly, your ear's not going to notice. That's lossy. Our process is zeroing in on the music in this big coding space, right? The sampling kernel has been picked, suited to music statistics, so we're looking at finite innovation rate, somewhere between environment and speech. It's appropriate for the human listener. We're not designing audio for mice. It's optimized for allowing us to separate out the reverberation, because how we know how far away something is, reverberation is an important clue. The system, and this is what's novel, genius, is we can make an encoder with an impulse response and a decoder with an impulse response, and you glue them together, and the impulse response is even shorter. And this is how we can get fine time information through a channel which appears to be running at a sample rate that is not as fast as you would expect for the performance. So we actually get performance within 1% of the uncertainty principle. I'll leave that to Peter to explain to you. The main thing is we come up with a lower data rate than either the sync or the Gaussian for the same blur. Think back to the cascade of filters. Everything we do will blur it a bit. The amount we blur it is not a lot. We've spent a lot of time in the last 3 years working on this, not as audiophiles in the corner thinking this is very cool. We've been working hands-on with recording engineers, mastering engineers, artists, producers. Give us your song, play it to them in their studio again and again and again. And the thing that surprised us the most was as we started to encapsulate the sound, asking, have we made it worse? They said, no, we made it better. It's more like the original analog feed. That's for another lecture. We understand some of it. Let's go back to our notional picture then of digital sound quality. What we're asserting is the encapsulation process allows us to capture the time resolution and frequency in important parts of the studio at a lower data rate. And even at 44, with infrared coding, it sounds like a 96 recording. You don't have to waste all this data to transmit the signal. And that's an example of the impulse response of the chain. So the conventional 192 chain, looked on a log scale, has an impulse response this wide. Ours is this wide. Maybe where the action is, it's this versus this. And blur doesn't rise until we get below 96 kilohertz. We're proposing a distribution method. You encapsulate it. We've got lossless buried data encoder, which passes the information forward. It's very simple. It's not difficult. Not difficult to implement. The file itself, which comes out of this encoding process, you put in PCM, you get out PCM, which answers the question that I'm asked most often: does it sound like FLAC? The answer is you can use FLAC to put it in. Actually, you can use anything else, but no, it doesn't sound like FLAC. It sounds like the original music. And here, showing a streaming variant, is the data rate concept. We can start with data at 52 megabits per second. encapsulate it, encode it losslessly, so that what was heard at the studio is delivered exactly at the far end, losslessly, and wrap it for streaming. The most exciting thing for us is that we can take the sound of the studio and encapsulate it into something that you can stream, in this case, 830 kilobits per second.
Do you mean kilobits or kilobytes?
Kilobits per second. Oh, sorry, I didn't want that picture. Okay, that's it. Thank you. Apologies.
Thank you very much, Bob and Peter. Well, I think that's all been quite thought-provoking. I'd like to open the floor to just a few questions. I'm afraid we don't have that much time left. If you could use the microphone just so that we can record all the speech. Any questions? Yes.
Hi, John Honeyball, Woodleyside. 30 years ago, almost exactly, I was in an AS lecture here in London, and Dr. Roger Lagardec broke the news to the world about pre-echoes, which came to a terrible shock to everybody from BBC and Analog World, who had never really thought about it that way before. And I remember the loud arguments with Peter Walker and Angus Mackenzie and so forth at the time, that this was a terrible thing and how had it come to be. It seems like the last 30 years, arguably, we've been going in directions that haven't been to the best. And I was fascinated, very fascinated by some of the topics that you raised this evening. What you haven't covered on here is how do we bring this to the customer, given that there are N billion CDs out there? How can we persuade them of the benefits of this and deliver this to them in a way that they will be happy to consume without forcing yet another format on the world? We have a history over the last 30 years of failed high-resolution formats after CD, and the last thing the public needs is yet another one. So what you haven't touched upon here is what can we do with our historical library, let alone moving forward. Obviously, moving forward is easy with new recordings, but what do we do with the huge libraries out there?
Do you mean consumer libraries or recording labels libraries?
Well, in a sense, both. We have got catalogues inside companies that go back to 44K 16-bit. We have got stuff that's better than that now, but we also have got customers out there with existing technology. How are we going to... Does this bring anything to them, or is this yet another step change in the market for these people?
It's another step, but we have it in hand. You may have picked up from Bob's talk that the infrared works down to 44 kilohertz. So there is the possibility of producing CDs that have a time resolution similar to 96 kilohertz. But then the world is also moving away from, just looking at the consumer market, the consumers are moving away from libraries of their own CDs. As we move to streaming, which gives much more flexibility for a new format. Well, Bob.
Yeah, we don't really want to call it a format because, as I mentioned, we're turning PCM into PCM. And so it can be distributed a number of ways. Tonight's lecture is about one aspect of a suite of technologies that we will be announcing fairly soon, this side of the autumn. Okay? And how it's going to come out, how it brought to market, we're not going to say too much tonight, except that we've been working very closely with the music labels because they've got all the music. And we're able to bring in any content of any sort, from 78s to analog tape to modern digital.
But the route to market these days will be Apple and Samsung. unfortunately.
Yes,
Okay.
that's fine. This isn't really. I was hoping not to have a commercial discussion tonight, but if you'd see me outside afterwards.
Will do, Bob. Thank you.
Yeah. But
I think Apple and Samsung, Apple will sell what's available, what's possible, at practically, and Samsung will make devices that will play it.
And I mean, well, it's even simpler than that because you can stream anything to a decoder that you download. So, this is about how you get the magic into the consumer space, right? Let's leave the rest to the other guys, but we were only tonight able to talk about frequency, not about many of the other aspects of the thing we've been working on.
Can I have a question from the gods? Can you hear me?
Yeah.
You've talked about this new method of encapsulation, which can reduce the bit rate of the signal down to some comparatively lower frequency, and yet preserve a very high audio quality. And what I'm not clear about is does the listener need specialised equipment, specialised converters in order to be able to read this? Is it just a matter of encapsulating the data, or is it also a matter of providing new equipment in order to decode it?
On the block diagram here, we show archive masters, existing equipment, existing A to D converters, existing DACs. This euphemistically named box, the replay manager, is the DAC manager. You don't need a new DAC, you don't need a new ADC. You just need to get the signal to the DAC.
So there's a sort of software block in your computer or microprocessor. Sorry, guys.
Yeah.
So if I've understood this right, there's a software block in the computer microprocessor or music player, whatever, Apple, Pono, whatever it may be, that recodes this thing so that a conventional chipset can then play it out with the kind of resolution you've planned.
There's no point in trying to bring something to the market that can't live in that world, because people have legacy world. They have Sonos systems, they've got cars, they've got CD players. You have to be able to play where it lives. It's also important to be able to give the very best quality when somebody wants it, but that's an option.
Hello, I'm Peter Adamson. I provided the Castanets record. Yes. And that leads me to a question which I feel wasn't quite clear in my own mind about. And that is that Peter quite properly honed in on the transient information from the surface noise of the record, which is clearly is or should be extremely short. Whereas the transient information from the castanets, as he also pointed out, was from sounds which were really quite band limited. Now, since you are talking about, if you like, precision of timing, I wonder if you could clarify the situation about timing of sounds which are not quite so blatantly transient as either Crackers on the 78 or the Castanets sound. And in particular, for instance, Peter knows that I've let him hear transfers of really quite old cassette recordings, which quite clearly sound much better at 96K than they do at the standard CD rate.
The Castanet recording is a poster child for transients that appear in the channel out of band. I mentioned things that can overload, and even in the perfect CD world, if you've got a dropout, you have a transient which is outside Nyquist. But because we're talking about impulse responses, doesn't actually mean we listen to transients. It's the timing information that we want. And my experience listening to high resolution is the thing that gets better as we put the resolution up is spatial information, where things are, how far away they are. If I played you, which I might in a minute, Take 5 by Brubeck, on the CD the symbol's big and splashy, and the higher the resolution is, the more precisely it's located so that you feel you can reach out and touch it. So these sounds, that's a symbol, it's another transient instrument. But it's true of everything. It's true on voice, it's true in the bass. I got into a lot of trouble for putting that in the AS journal, that high res made a difference in the bass. We still believe it because it's more articulate, because the modulation noises are different.
I think that's the thing about the piano, isn't it? That if you look on a spectrum analyzer, there's very little above 10 kilohertz on a piano, but what there is this very atmospheric noise of the velvet hammers on the string, velvet kind of brushing against the strings, and it kind of gives it the focus. And if you take that away, then it's just kind of glossified mush, really.
If you go back to what I was talking about how we externalize objects, our perceptual system is non-linear. You will hear something, and a small piece of information will switch it into a different percept. It's not gradual. Richard and I, when we were working on CD, we still remember it, sitting listening to Joan Baez actually playing guitar. And we were working on the CD player and we were fiddling, and we weren't doing green ink, but we were doing stuff to it. And we made one change, and suddenly we heard a zither. The problem with that is, once you've heard the zither, you always hear it. And so that's why you can't do A/B testing easily. You can do it, but not easily. And so these fine details that completely change the character, that change the location, the space, the room. There's too much blur, you don't know where the recording was made. If there's not, you can sense the walls very quickly.
Right, I think we probably have time for one more question.
Can I ask, the only way to actually take full advantage of what you're saying is to have a perfect reproduction system with two loudspeakers in an anechoic room, and you're supposed to be in the binomial bisector between the two speakers so that your ears actually sample the correct phases of the signals. Now, since it's not practical in most occasions, is it really worth the bother?
Oh, yeah.
I think the answer is that what you're saying is theoretically correct, but it doesn't seem to happen in practice. We do hear the differences very strongly in real situations and off-center.
The extraordinary thing about the binaural processor is it extracts sounds from the room. As soon as you speak, you know what the room's like. You play your system, if it's a reasonable speaker, it's mapped out of the room quite quickly. And none of us, I mean, hands up who listens in an anechoic chamber to music, right? You don't.
I think there's actually another point here that you mentioned, Bob, that just now, that if perceptual effective changes is not continuous, it's a sudden jump. That the result of that is that if a playback situation is already compromised, then it can take only a small extra degradation to flip you into, well, really, this isn't very interesting after all. So, in some ways, non-ideal conditions can actually produce make it easier to tell differences in reproduction quality than theoretically perfect. I mean, we've often found back in the old days that if you want to test an amplifier, you don't use a perfect recording. You use a recording that's already got tape saturation or something, and it's kind of on the edge of being all right. But there's small differences.
Nevertheless, the better the system, the better you'll hear it, and you will hear differently on headphones and speakers. That's an important thing. So you can always have a quest to a lower blur system. In fact, this, as you may have heard us talk about it, we think now is the most important parameter for a system, for a speaker or a whole chain, is not necessarily its frequency response, but how much does it stretch time. If you have a system which blurs a lot, you might find it very difficult to do an ABX test of the difference between CD and 96 or 192. We know because we tried that. But if your system doesn't blur, you can get valid results. And I don't think she's here, but one of our team is working with us. We're presenting a paper on that in LA to put at least one ghost to bed.
Okay, one final question, and then did you, Bob, want to play an example?
No, we're done.
No, you're done. Okay.
You said we had to be out by 9 o'clock.
You were talking about the infrared encoding. That's like the recording. In processing this kind of audio, would there be would you do it just the same as we do it now, except at 196?
We would tend not to use a typical DAC that will have a filter with a brick wall response, which does all the damage. You know, we've made it clean up to the recording. That would now do the damage. It would be better. I mean, it's okay to use. Right, you get some benefit using a conventional DAC, but it would be better to have a DAC which is also designed on rather similar principles, with kind of triangular reconstruction and some frequency response flattening. And that's what when I gave that, the slide of the end-to-end response, that's represented the total system of ADC, encoding filter, downsampling filter, upsampling filter.
You've hit on a point that I wanted to make, an important point I wanted to make, because here we're talking about Archive Master. What we've talked to you about is a coding system where we can get everything we can hear into a smaller box. The box is big enough to have something around it so it's not damaging that thing, but it's still a smaller box. Therefore, it's not necessarily what you'd use for an archive, because what you should put into the archive always is the very, very best thing you can do at any point in time, so that in 10 years' time or 15 years' time, somebody smarter than us will show you how to get even more out of it. It's quite improper at the moment that the music industry is thinking about shipping what it thinks of as its masters, because you should capture as much information as you can, and then not quite decide how much to give the customer, but what's appropriate. The idea that we can stream high resolution is extraordinary, and we will be announcing this as a kind of project and a program to come.
Right, I think that's probably all we have time for tonight. So I'd just like to say thank you again to both Bob and Peter.
Thank you.
I'm sure they'll stick around for a few minutes to answer any final questions. So we hope to see you again next month, where Trevor Cox will be speaking just down the road. So hopefully see you then.
Thank you all for staying late.